Look up at the moon tonight. The moon you are looking at is, on average, 384,400 kilometers away. That number has been measured so precisely by so many independent methods that we know it to within a few millimeters. We have known the rough figure for 2,000 years and the exact figure for 56. But here is what the precision of that measurement has revealed, and what the ancient astronomers who first asked the question could not have known. The number is changing. The moon you are looking at tonight is farther from the Earth than the moon your grandparents looked at. It is farther than the moon the Apollo astronauts traveled to. It is farther than the moon the dinosaurs would have seen. Every year, the gap widens by 3.8 centimeters, about the width of a credit card. It does not sound like much. Over geological time, it adds up to something almost incomprehensible. The moon is leaving. This is the story of how we figured that out, what is causing it, and where it ends. And to understand any of it, we have to start with a question that took human beings 2,300 years to answer precisely enough to notice the moon was moving at all. The question of how far away the moon is one of the oldest questions in astronomy. It is older than the telescope. It is older than the printing press. It is older in its precise form than the Roman Empire. The first person we know of who tried to answer it with a number was a Greek astronomer named Aristarchus of Samos, who lived in the 3rd century BCE. Aristarchus is the same astronomer who proposed 1800 years before Copernicus that the Earth orbits the Sun rather than the other way around. The sun-centered model did not take, but his method for measuring the moon did. Aristarchus reasoned as follows. During a lunar eclipse, the moon passes through Earth's shadow. By measuring how long the moon takes to cross the shadow and how long it takes to cross its own diameter, you can work out the ratio of the moon's size to Earth's shadow. By measuring how long the moon takes to pass behind Earth completely, you can work out how big Earth's shadow is at the moon's distance. Combine these measurements with a few assumptions about the sun's distance, and you can derive the moon's distance in units of Earth radii. Aristarchus arrived at a figure of between 62 and 67 Earth radii. The actual figure is 60.3 Earth radii. He was, to within the precision his instruments allowed, in the right neighborhood, off by perhaps 10%. Working with naked eye observations and a geometry his successors would spend the next 2,000 years refining. This is worth pausing on. 2,300 years ago, using nothing but geometry, sundials, and his own eyes, a man on a Greek island worked out the distance to the moon to within 2% of the correct answer. He did not have a clock. He did not have a telescope. He did not have algebra in the modern sense. He had the shadow of the Earth and the patience to watch the moon move through it. He also had no way to detect that the number he was measuring was not constant. The precision of his method was not high enough. That detection would take another 2 millennia of refinement, and it is the slow improvement of that precision across centuries, across instruments, across civilizations, that the rest of this story is really about. A century after Aristarchus, the Greek astronomer Hipparchus refined the measurement using a different method. He used parallax, the apparent shift in the moon's position when viewed from 2 different points on Earth. By coordinating observations of a solar eclipse from 2 cities, Hipparchus calculated the moon's distance more precisely than Aristarchus had. His figure was within 1% of the modern value. For the next 1,800 years, that was as good as it got. Ptolemy refined the method slightly. Islamic astronomers in Baghdad and Cordoba refined them further. But the basic approach, geometry, eclipses, parallax, remained the same. The moon was about 60 Earth radii away. Everyone agreed. Nobody could do much better. And at the level of precision available to anyone working with the naked eye, the distance looked perfectly constant from one century to the next. The next major leap came in 1751, when a French astronomer named Nicolas Louis de Lacaille traveled to the Cape of Good Hope in South Africa to coordinate observations of the moon with another astronomer named Jérôme Lalande in Berlin. They were measuring the moon's position against background stars from 2 points 8,500 kilometers apart. The geometry was the same as Hipparchus's, but the precision was vastly better. Lacaille and Lalande measured the Earth-Moon distance to within about 0.1%, still not precise enough to detect the recession. At 3.8 centimeters per year, you need to measure the distance to within a few centimeters before the change becomes visible against the noise. Lacaille and Lalande were measuring it to within a few hundred kilometers. They were closing the gap. They were not yet there. For 200 years after that, all improvements in lunar ranging were refinements of this method. Better instruments, better stellar catalogs, better triangulation. By the early 20th century, we knew the moon's average distance to within a few hundred kilometers. And then, in 1946, the United States Army bounced a radar signal off the moon. The signal took 2.56 seconds to travel from a radar dish in New Jersey to the lunar surface and back. The speed of light was known. The travel time was measured. The arithmetic was trivial. For the first time in human history, the distance to the moon was known not by geometry, but by direct measurement. A thing was sent to the moon. It bounced back, and we timed how long it took. The radar measurement was precise to within a few kilometers. Better than 2,000 years of geometry. Better than any astronomer working with telescopes alone could have hoped for. And still not precise enough to see the recession. A few kilometers of uncertainty drowns out 3.8 centimeters of annual change. The measurement that would finally cross the threshold required something different, not a chance reflection from the lunar surface, which scatters light in every direction and returns only a tiny fraction of what you send. A purpose-built reflector, engineered to send light back along the exact path it came in on, no matter what angle it arrived at, a device placed on the moon deliberately by a human hand. On July 21, 1969, Buzz Aldrin set one down on the Sea of Tranquility. It is still there. The device Aldrin deployed is called a corner cube retroreflector. It is a passive instrument. No power, no electronics, no moving parts. It is a panel of 100 small glass prisms, each shaped like the inside corner of a cube. When light enters a corner cube prism, it bounces off the 3 internal faces in sequence and exits parallel to the path it came in on. Regardless of the angle of entry, the light returns to its source. This sounds simple. It is simple. It is also one of the most consequential pieces of hardware ever placed on another world. The Apollo 11 retroreflector was the first of 5. Apollo 14 deployed a similar panel. Apollo 15 deployed a larger one with 300 prisms instead of 100. The Soviet Lunokhod 1 and Lunokhod 2 rovers carried French-built retroreflector panels and placed them at 2 other lunar locations between 1970 and 1973. 5 retroreflectors at 5 different sites on the moon, all functioning continuously for more than 5 decades. Here is what we do with them. At observatories around the world, the Apache Point Observatory in New Mexico, the Côte d'Azur Observatory in France, the McDonald Observatory in Texas, the Matera Laser Ranging Observatory in Italy, we fire a laser pulse at one of the retroreflectors. The pulse leaves the observatory as a beam a few meters wide. By the time it reaches the moon, after a journey of about a second and a quarter, the beam has spread to about 7 kilometers across. Only a small fraction of the pulse hits the reflector. Of that fraction, the reflector returns essentially all of it back along the original path. By the time the returning pulse reaches Earth, it is spread to about 20 kilometers across, and the observatory's telescope catches only a handful of the original photons. A few photons. After traveling 768,800 kilometers round trip. That is what we measure. The travel time is recorded to within a few picoseconds. Multiplied by the speed of light, this gives the Earth-Moon distance to within about 1 millimeter. We know the distance to the Moon, in real time, to a precision smaller than the width of a thumbnail. We have been making this measurement continuously since 1969. 56 years of data, tens of thousands of individual range measurements, the longest-running, highest precision distance measurement humans have ever made of any object in space. And what the data shows, unambiguously, is this. The distance is increasing. Each year, the measured average distance to the Moon is 3.8 centimeters greater than it was the year before. This is not a theoretical prediction. It is not a model output. It is a measurement. We send laser pulses to a reflector that has not moved relative to the lunar surface in 50 years, and each year the round-trip time is slightly longer than it was the year before, by an amount that corresponds to 3.8 centimeters of additional distance. 3.8 centimeters per year. A meter every 26 years. A kilometer every 26,000 years. The Moon is leaving slowly at a rate that an ordinary human lifespan cannot perceive, but that the precision of a laser bouncing off a mirror on the Sea of Tranquility has rendered absolutely visible. The next question is the obvious one. Why? The answer is tides, not the tides as a metaphor. The tides. The same tides that flood the salt marshes twice a day and strand boats in harbors and have shaped every coastline on Earth for 4.5 billion years. The mechanism that pushes the Moon away from Earth is the same mechanism that pulls the ocean up the beach. Here's how it works. The Moon's gravity pulls on the Earth. It pulls hardest on the side of the Earth facing the Moon, less hard on the center of the Earth, and least hard on the side facing away. The difference between these pulls is what we call the tidal force. It stretches the Earth slightly along the Earth-Moon axis, raising a bulge of water on the near side and another smaller bulge on the far side. As the Earth rotates underneath these bulges, any given point on the surface passes through both of them each day, which is why most coastlines experience 2 high tides every 24 hours. So far, this is the standard explanation of how tides work. The interesting part is what comes next. The Earth rotates once every 24 hours. The Moon orbits the Earth once every 27 days. The Earth, in other words, spins much faster than the Moon orbits. And the water bulge raised by the Moon does not sit perfectly along the Earth-Moon axis. The Earth's rotation drags the bulge forward ahead of the Moon's position by a small angle. This matters because the bulge has mass, and mass has gravity. The bulge of water, displaced slightly ahead of the Moon by the Earth's rotation, pulls the Moon forward in its orbit. The Moon, in turn, pulls back on the bulge and through the bulge on the rotating Earth and slows the Earth's rotation. The result is a transfer of angular momentum. The Earth is losing rotational energy. The Moon is gaining orbital energy. And by the conservation laws that govern orbital mechanics, a Moon that gains orbital energy moves outward away from the body it orbits. This is what is happening every day on a planetary scale. The oceans are functioning as a vast gravitational gearbox, taking energy out of Earth's rotation and feeding it into the moon's orbit. The day is getting longer. The moon is getting farther away. The two changes are linked. They are the same process viewed from different sides. The numbers, when you work them out, are striking. Earth's day is lengthening at approximately 1.7 milliseconds per century. This sounds vanishingly small. It is also measurable, and it has been measured. Ancient eclipse records from Babylonian, Chinese, and Arab astronomers give us datable astronomical events going back nearly 3,000 years. When modern astronomers calculate where those eclipses should have been visible, assuming a constant Earth rotation, the calculations are wrong. The eclipses were seen in different places than the math predicts. The discrepancy is consistent with an Earth that has been spinning slightly faster in the past and slowing down at exactly the rate that the lunar laser ranging measurements predict. The Babylonians could not have noticed any of this. The change is too small to detect over a human lifetime, but their records, written down on clay tablets and preserved across 3 millennia, contain the evidence that the change has been happening continuously the entire time. We read it now, with measurements they could not have made, and find that the Earth has been slowing down at exactly the rate the laser ranging predicts. Over geological time, the accumulation becomes extraordinary. 600 million years ago, in the Ediacaran period, the Earth's day was about 22 hours long. This is not a guess. It is recorded in the growth bands of fossilized corals and in the layering of tidal sediments called tidal rhythmites, which preserve a daily and monthly record of tidal cycles in stone. The rhythmites from the late Precambrian show a year of approximately 400 days, each day approximately 22 hours long. The moon then was closer. 1.5 billion years ago, the day was about 18 hours long. The moon was substantially closer, close enough that solar eclipses, when they happened, would have been longer and more total than any eclipse a human has ever witnessed. 4.5 billion years ago, when the moon first formed from the debris of a collision between the proto-Earth and a Mars-sized body we call Theia, the moon was perhaps 15 times closer than it is now. It would have filled an enormous portion of the sky. The tides it raised on the molten early Earth would have been hundreds of meters high. The day then may have been as short as 5 hours. The entire history of the Earth-Moon system has been a slow separation. The moon has been leaving for 4.5 billion years. We are watching the late chapters of a very long departure. The natural question is, where does this end? If the moon is moving away and the Earth's rotation is slowing, both processes have to stop somewhere. The conservation of angular momentum requires it. You cannot keep transferring energy from Earth's spin to the moon's orbit forever, because eventually there will be no spin left to transfer. The endpoint, if you let the system run, is called tidal locking. It is the state the moon is already in with respect to Earth. The moon rotates exactly once per orbit, which is why we always see the same face of it. The far side of the moon was unknown to humans until 1959, when a Soviet probe finally photographed it, because no point on Earth had ever been positioned to see it. The moon is gravitationally locked to the Earth in a 1-to-1 resonance. The endpoint of the current process is a state where the Earth is locked to the moon in the same way. Earth's day would equal the moon's orbital period. Both would equal approximately 47 of our current days. The moon would hang motionless in the sky over one hemisphere of the Earth, never rising and never setting, visible from one half of the planet and permanently invisible from the other. The tides, in the sense we currently understand them, would stop. The transfer of angular momentum would stop. The moon would stop receding. This configuration is mathematically stable. It is also, when you work out the timescale, approximately 50 billion years in the future. The Earth-Moon system will not reach it. In approximately 5 billion years, the Sun will exhaust the hydrogen in its core and begin burning hydrogen in a shell around the core instead. This change will cause the Sun to expand. Over the following 1 to 2 billion years, it will swell to many times its current radius, becoming what astronomers call a red giant. Its outer atmosphere will extend past the current orbit of Venus. It may or may not reach the current orbit of Earth, depending on details of stellar mass loss that are still being worked out. But the question is academic. Long before the Sun's surface reaches the Earth will be uninhabitable in every sense that the word can carry. The oceans will boil. The atmosphere will be stripped away. The surface will melt. The moon by then will have receded by tens of thousands of kilometers more. The exact figure depends on how the recession rate slows as the moon moves outward and the tidal coupling weakens, but the moon will still be far short of the stable configuration the system is reaching for. It will be slightly farther away than it is now. It will still be leaving. The tidal locking that would eventually stop the recession is 45 billion years past the point at which the Sun ends the experiment. The moon will never finish leaving. This is a strange thing to sit with. The moon has been moving away from the Earth for 4.5 billion years. It will continue moving away for another 5 billion, and it will be cut off mid-departure by the death of the star that lit both bodies for their entire shared history. The process that has shaped the Earth-Moon system since its violent birth will not run to completion. It will be interrupted. There is no version of the future in which the moon comes back. There is no orbital mechanics that returns it. The angular momentum that has been transferred from Earth's spin to the moon's orbit cannot be transferred back. Even if the Sun did not interfere, even if the Earth-Moon system were left alone for 100 billion years, the moon would only continue to recede, slowly, asymptotically, toward a final configuration it would approach but never quite reach. The moon you see tonight is the closest the moon will ever be again for the rest of the history of the universe. It is also farther away than it has ever been before for the entire history of the Earth. Every moon every human has ever looked at has been a moon that was leaving. The moon that Aristarchus measured from Samos in the 3rd century BCE was closer than the moon overhead tonight by about 80 meters. The moon that the Apollo astronauts traveled to in 1969 was closer than tonight's moon by about 2 meters. The moon your grandparents saw was closer than yours. The moon your grandchildren will see will be farther. The distance is small. The direction is not. There is a phrase in geology, deep time, that refers to the time scales over which planets and continents and species change. It is the time scale on which mountains rise and erode. It is the time scale on which oceans open and close. It is the time scale that human intuition is not built to handle. The recession of the moon happens in deep time. 3.8 centimeters per year is not a number a human lifespan can perceive. We can measure it with a laser pulse, and we can extrapolate it across billions of years, but we cannot feel it. The moon you saw last year and the moon you see tonight are, to your senses, identical. The change is real, but it is hidden by the slowness of the change. This is the condition of most of the universe's most interesting processes. The continents drift at the speed your fingernails grow. The sun is converting hydrogen to helium at a rate that, on human timescales, looks like an unchanging fire in the sky. The galaxy is rotating. The universe is expanding. None of these processes are visible to us in the moment. They are all visible to us in the accumulated record of measurement. The moon's recession is one of the small set of cosmic processes we have caught directly, not inferred from theory, not extrapolated from indirect evidence, measured year after year by laser pulses bouncing off a panel of glass prisms on the Sea of Tranquility that Buzz Aldrin set down on July 21st, 1969. The retroreflectors were not deployed for this purpose. The Apollo mission planners included them as a way of testing whether the technique would work at all. They expected the reflectors to function for a few years before being degraded by lunar dust or thermal cycling. The reflectors are still working 56 years later. They will, almost certainly, still be working 1,000 years from now. They are passive optics on an airless world. There is nothing on the moon to wear them out. 1,000 years from now, if humans are still firing lasers at the moon, the round-trip time will be longer by about 250 nanoseconds. The moon will be 38 meters farther away. The measurement will still be possible. The reflectors will still return their handful of photons. The departure will still be in progress. 1,000,000 years from now, the moon will be 38 kilometers farther. Solar eclipses, which depend on the moon being almost exactly the right size and distance to cover the sun's disk, will be slightly less perfect than they are today. We live in a narrow window of cosmic history during which the angular diameter of the moon and the sun, viewed from Earth, are almost exactly equal, close enough that the moon can blot out the sun's disk and reveal the corona during a total eclipse. This coincidence is not permanent. The moon used to be too big in the sky to produce the eclipses we get today. In the far future, it will be too small. Total solar eclipses in the form we experience them are a feature of this particular geological moment. They did not always exist. They will not always exist. Tonight's moon, the one you can step outside and look at, is in the middle of a 4.5 billion year departure that will be interrupted by the death of the sun before it can be completed. It is closer than it will ever be again. The light reaching your eyes left the lunar surface 1.28 seconds ago. The reflectors on the Sea of Tranquility, the Fra Mauro Highlands, the Hadley Apennine region, and the 2 Lunicod sites are still there, waiting for the next laser pulse from the observatory in New Mexico that will measure the gap one more time and find it 3.8 centimeters wider than the year before. The moon is leaving. It has been leaving since before there were oceans on Earth. It will be leaving when the oceans are gone. The only thing that changes year by year is the size of the gap. Look up at it tonight. This is as close as it will ever be again.